Welcome to your OMG video on stopping and safety. Okay, so we're going to be looking at stopping distances, and then we're going to look at safety devices in cars and how, well, vehicles are designed to keep us safe. And then there's a little bit about the efficiency of vehicles. Okay, so the first things first, I'd like you to pause the video and think about how, what are the stages of stopping a car. Okay, you can also think about it in terms of stopping your bike. Okay, pause video when you're ready. Go on to the next stage, okay? So, the stage of stopping a car, all right? So we're driving along, we see a hazard escape, so it's a person in the road or brake lights ahead. We think about stopping. We've got to process what we see before we start putting the brakes on, okay? This would be our thinking distance, all right? So these two. Thinking distance, okay? All right, and then the next three, putting on the brakes, the car slowing down and the car stopping. Okay, so up until that point, these are our, sorry, not stopping, this is our braking distance. Okay, so as soon as we see the hazard, okay, whatever it is that we think, oh, that's going to make me want to stop, okay, that's the thinking distance. Okay, as soon as you start putting the brakes on until the car stops, that's the braking distance, and then that total distance, so if we add the thinking distance to the braking distance, that total distance is the stopping distance. So we have the stopping distance equals thinking distance, okay, plus braking distance. Okay, all right, so stopping distance equals thinking distance plus braking distance. Okay, so this is a diagram taken directly from the highway code. Okay, so you can see that our stopping distances at the end here, okay, it measures in meters, feet, and then car lengths. Okay, so car length is an approximation because all cars are slightly different lengths. Okay, it's an approximation. So these distances are much more useful, okay? Obviously, when you're driving a car, you can't get out and measure the distance, so you rely on estimating how far that distance is. So using the car length is just a way of estimating, okay? So we can see that as our velocity increases, as our speed increases, our thinking distance increases, okay? Now, if we look at the braking distance, that also increases, okay? Remember, thinking distance is the distance travelled between seeing a hazard and applying the brakes. Braking distance is between applying the brakes and coming to a complete stop. Okay, so you can see at 70 miles an hour, the national speed limit, 24 car lengths or 75 meters. Okay, so 100 meters is obviously how far you would sprint on sports day or in PE. Okay, so let's have a little bit of a closer look at that. Okay, so obviously this total distance is the stopping distance, is the thinking distance plus the braking distance. Okay, so let's have a little bit more of a detailed look at that. Okay, so let's look at the thinking distance first, the blue part. Okay, so as the speed of the car increases, the distance it travels increases at a steady rate. Okay, so if I double my speed from 20 to 40, the thinking distance changes from 6 to 12. So that doubles. So it's a constant rate. So from 30 at 9 meters to 60 at 18. Okay, we've doubled, and that's doubled. Okay, now the thinking time, okay, we've assumed is staying the same, okay, but the distance is going to increase because your speed is increasing, okay? If we look at braking distance, the speed the car increases, kinetic energy increases as a square of the velocity, okay? So we already know that KE is proportional to V squared, okay? So if you double the velocity, you quadruple the kinetic energy, okay? So we can prove that by having a look at this. So from 20 miles an hour, we've got 6 meters braking distance. Okay, if we double that to 40, we get 24, okay? So if you double your speed, 9 to 18, 14 is pretty much 55 meters, okay? This is because the velocity is obviously, the velocity is squared for kinetic energy, okay? The brakes have to do more work to slow the car down. They transfer the kinetic energy into heat energy, and that means the distance it takes to slow to a stop is increased, okay? So it's very important that we recognise that doubling your velocity doubles your thinking distance and quadruples, so a factor of 4, your braking distance, okay? And then we add those two values together to give us the total stopping distance, okay? Okay, sorry. Right, factors affecting stopping, okay? So these are the factors that affect stopping, okay? You may be asked in an exam, okay, explain or give 3 ways that stopping distance can be affected, okay? Some of them affect only thinking distance, so alcohol, and it's important that you say increases thinking time, okay? So you're saying that the time it takes you to react to a stimulus is being increased, okay? So it's going to increase your thinking distance, and that increases your stopping distance, okay? So you say it increases thinking time, okay? So if we look at another one, passengers, okay, distractions, they will increase your thinking time, okay? Drugs, increase thinking time, therefore increase total stopping distance, okay? Mobile phones, it's a distraction, it increases your thinking time. Total stopping distance is affected. Speed, okay, affects both, okay? So it increases the amount of distance you travel, yeah, so the time stays the same, but it increases the distance you travel when you're thinking. Tiredness, increases reaction time, okay, or thinking time, yeah, so it's increased the time, okay? For those that affect braking distance, okay, it's important to say it reduces friction, okay? So I've said worn tyres or worn brakes or tyres and brakes in bad conditions. It increases the braking distance because it's reduced friction, okay? Here we can say icy roads, reduce friction with road, okay? You can't just say weather. Yeah, we need to say the road is icier or the road is in a poorer condition. Yeah, it's a damaged road surface, poor weather, okay? Reduce friction with road, reduce friction with road, okay? Here we're talking about passengers. We could say mass, okay? There's more mass. Therefore, we'd have to provide more force and more work needs to be done to stop the vehicle, which increases our total stopping distance, okay? And again, speed, again, like passengers, it increases both the thinking and the braking distance, so it increases the stopping distance, okay? Right, so moving on to vehicle safety. Modern vehicles have a range of safety features, okay? They are designed to keep us safe inside the vehicle, okay? In the event of, it reduces the likelihood of injury, okay? It reduces the likelihood of death in a collision, okay? So we've got airbags, crumple zones and seatbelts, and they're all designed to deform, okay? They are designed to increase the amount of time you are in a crash, okay? And that may sound counterintuitive, but we do that to decrease the amount of force, okay? And I'll show you the maths behind that in a second, or the physics behind it. So the other end of those safety features is the safety cell and the side impact bars, okay? So here's our side impact bars, and the safety cell is everything around you, okay? So the car is designed not to deform so that you don't get crushed, okay? So imagine your car rolls over or you get struck from the side. We don't want the car to crush us. We don't want the car to collapse when it's upside down. We don't want something driving into the side of us and physically injuring us, hitting us, okay? That's a slide. Let's get back to it. So there's a slide that shows everything you need to know, okay? So it says here about the engine block. Okay, that's designed to go underneath the passengers, okay? Here you can see the safety cell really clearly, a really strong cell that's going to reduce injuries by stopping things from getting in. We've got crumple zones at the front and rear. They're designed to deform, okay? So they are, the car is designed to brake to keep us safe. We've got airbags, okay? So there's an explosion that fills the airbag with gas, okay? And then because you're wearing a seatbelt, your head will hit the airbag as opposed to hitting the steering wheel, okay? The seatbelt, okay, that's designed to stop you from flying forwards and hitting the windscreen or hitting the steering wheel, okay? Obviously, that stretches and increases the amount of time it takes to stop, as does the airbag. That increases the amount of time it takes to stop, okay? We've got safety glass, okay, that's designed to shatter into tiny round pieces so that there's less likelihood of being cut by those, okay? Anti-locking brakes, okay, so that you're able to, if you put the brakes on, you start skidding, you're able to drive around an object, you still have control of the vehicle, okay? I think that covers everything. Oh, side impact bars, as we said earlier, okay? So here's some of the features, how they work. Okay, it's important to remember these things because they'll be the points that you'll be talking about in an exam question. I've just realised we've missed. We're talking about safety. Okay, now we can talk about vehicle efficiency. Okay, there are 4 ways to increase vehicle efficiency. Okay, we can reduce the air resistance by making the vehicle more streamlined. So think about a Formula 1 car or a sports car as opposed to a van. Okay, there's less work done pushing against the air. Okay, reduce rolling resistance by keeping the tyres pumped up. Okay, if you ever tried to ride a bike with flat tyres, you know it's very difficult. You have to put in a lot more work. Okay, that's because you're working against the tyre and you're deforming the tyre, so you're forcing yourself against that elastic tyre. Okay, reduce idling losses. So idling is when the car is at rest. Okay, but the engine is still running. It's using fuel, but you're not going anywhere. So you can switch the engine off when you stop. And that stops fuel from being wasted. Or modern cars have an eco setting where the engine will automatically turn itself off. Okay, and reducing mass. Okay, so inertial losses. Talking about inertia, we know that the greater the mass a vehicle has, the more difficult it is to change its movement. Okay, so having a lower mass vehicle, there's less inertia, so less force and energy are needed to accelerate them. Okay, right. Thank you very much for watching. Please answer your OMG questions, and thank you very much again. Yeah, cheers.